we started asking this question rather than centralized manufacturing. And the reason there is such a large gap is because you cannot just scale up these large scale factories because of the extrusion process that's used in melt blown polymer. What could be done if a single small scale factory could make between a material for 1,000 to 10,000 masks? That's why it's called 1,000 by 1,000, because you would have the capacity. If you have 1,000 of these factories, you would have the capacity to make between 1 million to 10 million masks globally. And this is what we started with. At that time, in the lab, we were brainstorming, and I started thinking about cotton candy machines. So this is the Amazon page for, this might sound whimsical, but literally we have built a solution that allows us to make N95 grade materials using a cotton candy machine. The idea is fairly simple. The physics of centrifugal melt spinning allows you to take inertial jets from centrifugal forces and spin them out into nanomaterials. This has been previously demonstrated for biological filament materials, and we started thinking about, could we use this type of a process to actually manufacture an N95 fabric? And that's what we did. To the left, you see a cotton candy machine where we are putting molten polypropylene nuggets that are molten and spun between 3,000 to 5,000 RPM. To the right, you're seeing a Van de Graaff generator. As many of you know, charge is incredibly important in making these electrode type materials that cause N95 base filtration. To the right, you can see the nozzles that are making these fabrics and sheets that are being spun out. And at this point, we have the capacity from a throughput perspective. You can see the material that's been produced to the right bottom. So we have still more experiments to do, but we are getting very close to essentially designing a factory in a box that allows us to engineer the parameters to be able to make a very large variety of filtration fabrics that could be used in masks. And especially when you realize that masks are not just used in health settings where the breathability is low, but you might want to tune the capacity to be able to make masks for the general public that still have a higher efficiency. And of course, again, do this in the middle of nowhere, for example, in Iquitos, in the jungle, in the Amazon. One of the joys of thinking about this work has been the replication of this work. When we started doing much of this work, we made Google Docs that we shared all of our work publicly, and we started noting that groups around the world started replicating it. So in this picture, you see the particle filtration setups and the pressure drop setups. And when we shared this work, literally groups started popping out in national labs in the US, all the way to Japan, several groups in India, several groups in Israel that started building these setups. And I got this video a couple of days ago from a group in Israel who had both replicated the setup the day we posted our documents, and at that same time shared the kinds of materials and experiments that they're starting to do with these systems. So this brings me a lot of joy in terms of thinking about engaging the broader communities in starting to experiment, and especially being able to do experiments at a global scale. So this is where we are in manufacturing of this kind of a material. And again, this is the work in progress. But I am excited about what it means from a context of distributed manufacturing and technology transfer. And especially all of the work in the lab from a COVID context is open source. So anybody can build upon this work as long as they follow the open hardware licenses.